Okay, in the previous video, I introduced the idea of boiling point elevation number, and the abbreviation was this little bit of a mess here, delta T sub B. And this number, again, just to sort of circle back, this is how much the boiling point goes up if you start dissolving some non-volatile things into your liquid. So if the boiling point of pure water is 100 degrees Celsius and I throw a certain amount of table salt or a certain amount of sugar into the pure water, the boiling point is going to go up, and let's say that it goes up to 103 degrees Celsius, then the boiling point elevation number would be 3 degrees Celsius for the amount of stuff that I dissolved in the water. And if I threw more stuff in, the boiling point elevation would go up even more. There is a formula that lets you estimate how much the boiling point elevation goes up. And it's written here. It's not too crazy, but this is the amount that the boiling point goes up is equal to some number, which I'm going to call K sub B, times some other number called M. K sub B has a really fancy name. It's called the ebullioscopic constant, but most people just call it the boiling point elevation constant. And that's probably what I'll call it, or I'll just call it K sub B. And K sub B is just what this means, empirically determined. It means that someone had to do a bunch of experiments to figure out what this number is for different liquids. It's a different number for different liquids. I certainly don't expect you to know what it is for water or any other kind of liquid. It'll be a certain number for water, it'll be a certain number for certain kinds of vegetable oil, let's say, certain number for certain alcohols. It'll be a different number for different liquids. And empirically determined just means you can't just think about it and figure out what the number is going to be. You have to do experiments to figure out what the number is. And so for water, the ebullioscopic number, or the boiling point elevation constant, is 0.52 degrees Celsius per kilogram per mole. And the units are really weird, but the units are there only to make this equation work out correctly. They're just there to have the correct units cancel. So that's what the K sub B number is. The M number is also a little bit weird. It is the solute concentration. Remember, solute is the stuff you're dissolving. It's the concentration of the stuff you're dissolving, but in these weird units called molality units. So what the frig is molality? It sounds like molarity, which we've covered in a previous semester, but it's not molarity. And I'll talk about what molality is on the next slide. But the point I want to make is that if you can figure out what the concentration of stuff is that you dissolved in these weird units, and plug that number in there for M, and if someone tells you what the boiling point elevation constant is, you plug that in there, you can multiply these two numbers together, and it'll give you a pretty good estimate for how much the boiling point is going to go up. It's not a perfect equation. It works when the concentration of stuff you're dissolving is kind of low, but it works reasonably well, and it's a pretty good estimate. So what is molality? Molality is another way of describing concentration of something you've dissolved in a liquid, let's say. Molarity, which is not the same thing as molality, if you remember from previous semester, it's the number of moles of stuff you dissolved, number of moles of solute per liter of solution. Molality is close to that. It is the number of moles of stuff you dissolved per kilogram of, per kilogram of liquid that you're dissolving into. So solvent means liquid alone. And so if we want to compare molarity and molality, the top number is basically the same. It's number of moles, although you'll see there's a wrinkle there too. The bottom number is not. For molarity, it's liters of the entire mixture. For molality, it's how much the liquid weighs that you've dissolved into in kilograms. And like I said, there's a wrinkle with the top number here. Number of moles of solute is not quite right. what it is what the numerator should be is the number of solute particles. And you might be saying, well, what's the difference? If you dissolve, let's say, table sugar, let's say that you dissolve 1 mole of table sugar into water, nothing really happens when the table sugar dissolves. It's still going to be 1 mole of sugar molecules in the water. But if you take 1 mole of table salt and dissolve it in water, the sodiums and the chloride ions split apart from each other. And what this means is for every 1 mole of table salt you dissolve in, there's 2 moles of particles, because the sodium ions and the chloride ions are separated from each other. So the amount, the number that goes in the numerator will depend on if your material breaks apart into ions, usually, when you dissolve it in your liquid. If it doesn't break apart into anything, like table sugar when you dissolve it in water, then the number of moles, the number that goes in the numerator here is just going to equal however many moles of stuff you throw in. But if it's something like table salt that breaks apart into different particles when you dissolve it in water, you have to count up how many things are actually running around all by themselves in the liquid. So for the case of table salt, it would be 2 particles for every 1 table salt molecule, let's say, that you throw in. So let's go back and look at this equation here. What this equation here is saying is this is some number for one particular liquid. This is some number that's never going to change. It's just some number that you have to look up or somebody has to tell you. So that's just some number. This number is concentration, so how much stuff you dissolved into your liquid. And the idea here is that if this is some number that never changes, but I make this number, if I make the m number get bigger, then this number is going to get bigger too, because I'm just taking some number and multiplying it by a bigger m number. And so what this is saying is, if the concentration of my stuff goes up when I dissolve it in the liquid, the boiling point is also going to go up even more. If the concentration of my stuff that I'm dissolving in the liquid goes down, then these two numbers multiplied together are going to go down, and that means the amount that the boiling point goes up is going to be less. So that's what this equation is doing. The K sub B number, the boiling point constant, boiling point elevation constant, is just some number that's not going to change. But the amount of stuff you dissolve, which is going to be shown by the m number, is going to control how much the boiling point goes up. There's a very similar equation for how much the freezing point goes down, and here it is. So again, remember, this is how much, this is called freezing point depression number. And so just to use water as an example, pure water, under the conditions we are used to, freezes at about 0 degrees Celsius. But if I dissolved some table salt or some table sugar into my pure water, freezing point would go down. It would be harder to freeze the stuff. So maybe it goes down to -4 degrees Celsius. And if that was true, then I would say the freezing point depression for my liquid would be -4 degrees Celsius. And again, there's a formula that lets you estimate what the freezing point depression might be. Here it is. It's -1 times some other special number, which is called the cryoscopic constant, but most people call it the freezing point depression constant. And this is just some number for different liquids. You have to look it up. Times the molality, again, of the stuff that you dissolved in your liquid. So same general idea as the previous equation, except there's a negative sign thrown in. And it'll be a different number for different liquids again, and I don't expect you to know what those numbers are, because I certainly don't remember what they are. In case you care, this is the freezing point depression constant for water, but it'll be a different number for other liquids. And m, this little m here, is molality again. And again, just to emphasize, this equation is an estimate, but it works reasonably well for a lot of different liquids and a lot of different things that you dissolve. So that's it for freezing point depression and boiling point elevation. In the next video, we're going to work through a problem where we're going to estimate one of these things. I don't remember which it is, though. All right, see you in the next video. Bye-bye.
Amo te, solo te, amore mio, ogni giorno di più mi innamoro di te. Amo te, solo te.